It's a great pleasure and an honor to come talk to you. I view the science teachers such as yourself as the people on the front line of this issue and the people who we researching scientists need to reach out to. And I will tell you, during the introductory comments, I heard some of the feedback that people are a little reticent, reluctant to talk about this issue. You might get pushback from parents, from students, and I certainly appreciate that. Every time I do a major media report, I am guaranteed to get pushback. And every time I get a letter without a return address, I know it's hate mail. But for every piece of contact that I get that is mean-spirited, I get 10 that are positive. So we've got your back. We scientists, we are here to support you because you are doing the important job. Just to comment on the kinds of things the rapid response team does, you heard about Jim Hansen's new paper. My organization interacts with mainstream media to try to explain science. And so we had a number of people who gave stories on the Jim Hansen paper. I, along with a colleague, Kevin Trenberth, appeared in the LA Times today, talking about the Jim Hansen paper and some of the consequences of that study. So our organization, gets scientists out talking to the general public, if it's through print media, website interviews, television, or radio. But what I want to talk to you today, about a number of things. First of all, I want to talk about the science. I'm going to show you all the science that we know. It's the current up-to-date science, and I'm going to cover all the major bases. I don't want to get too deep in the weeds of the details. I'm going to focus on an overview, because that's what we're most interested in when you talk to your students and families. I am going to have a message of hope, because there is something we can do about it. And if we take smart action, we can not only help the environment, but we can create jobs. We can improve national security. We can diversify our energy supply. So there's a bunch of reasons for taking action aside from just the environmental aspects. I am going to give you some pointers on how to deal with a hostile crowd. So I train scientists to give speeches and interviews in all types of venues. And there are some simple messaging techniques that we use to deal with the dismissive or the skeptical audience. And then finally, my contact information. Please feel free to contact me. If you have a student or a parent, or you just heard something that doesn't make sense, or you want some clarification, call me. Send me an email. Email is generally better. That's my office number. But without any more background, I'm going to get right into it. So these are the major topics I want to talk about. How certain are we? What do we not know? What do we know? What's going to happen? And what can we do about it? So I do have to put a bit of motivation in for this talk. We all are motivated to talk about this issue for a variety of reasons. This is one of the motivators for me. This is a photograph that I found when I started giving my talk around 2007. And it's a child holding a globe with the continent of Africa facing the photographer. Now that is important for a couple reasons. First of all, social equity. The parts of the world and peoples of the world who did not largely cause the problem will disproportionately suffer. Africa being a prime example. This photograph has taken on more personal meaning for me recently, because the middle finger of that child, the left hand, ends on the continent of Uganda. And my wife and I returned in March this year with our adopted daughter from Uganda. And she was born in a country that is being affected now by climate change. So it's almost like I knew I was going to adopt a child from Uganda when I got this photo. So how many of you have heard there's a debate? Yeah, come on. We've all heard there's a debate. Now, let me tell you something. In the science circles, there's no debate. I'm actually going to show you some facts that every scientist agrees on. There's no debate about these facts. Humans have caused a 40% increase of carbon dioxide. By the way, for the organizers here, I'm happy to leave my slides with the organization so people can get copies, use them however you want. There's no debate. We know humans have caused a 40% increase. We've known since 1856 that carbon dioxide was a greenhouse gas. This isn't new. This isn't something we learned in the last decade. We know the Earth has warmed in the last 100 years. The atmosphere has warmed. The oceans have warmed. In fact, that's what I study, oceanographic thermal monitoring. The Earth is warmer than it's been in probably more than 2,000 years. Greenhouse gas levels higher than 800,000 years. The Arctic is losing ice. The poles are warming. Glacier ice loss. And the ocean is becoming more acidic. Now, that actually is one of my biggest concerns. You think about a soda can. It's called a carbonated beverage because carbon dioxide is in the liquid. That's happening to our oceans. Now, why do we care? Well, we care if we eat or rely upon a food chain that goes to the base of the food chain of the ocean, because anything that makes a shell has a harder time making a shell and keeping a shell in an acidic ocean. So ocean acidification is another issue. Those are facts. Now, what do we do about those facts, or how do we interpret them? 97% of the most active climate scientists look at those facts. They're connected. I think that they're related to each other. The facts that we've increased greenhouse gases, and the fact that greenhouse gases should warm the planet, and the fact the planet has warmed, that makes sense as a consistent story. It's like a crime scene. If you watch like CSI, isn't that a crime show? Come on, does anyone watch CSI? Okay. You see someone walking down a hallway in a video camera with a gun in their hands. Then a door to an apartment is broken into. The fingerprints are on the doorknob. A body in the apartment with a bullet wound matching the gun. The gun is found in the perpetrator's car, and blood is in their apartment. Now, they may say, you didn't see me pull the trigger, you can't prove it. And that's true. In the same way, I can't prove all these facts are connected. But what is the standard of evidence that we use in our daily practice? If these things are all occurring, it makes a lot of sense to take action, because it takes mental gymnastics to disconnect them. 97% of the most active climate scientists say they are connected. 2% say we don't know, let's keep watching. And 1% says, I think they're unconnected, go home and have a beer. So that's the breakdown. Now, it turns out that the general public thinks there's a debate, but that's because this so-called debate or faux debate has been foisted upon us by outside organizations. It's not just that the planet's warming. That's not why we know we're the cause. It's that it's warming in the right way. There are fingerprints that tell us it's humans. Let me give you an example. By the way, these are fingerprints. You see one in the upper left, cooling of the upper atmosphere. If the sun were the primary cause of the warming we see, which some people say, it's the sun, John, it's the sun. If it were the sun, we would expect the entire atmosphere to warm because sunlight goes through the entire atmosphere. And we would also expect days to warm more than nights. That's when the sun's shining. We've observed the opposite. We've observed the upper atmosphere is getting cold, the lower atmosphere is getting hot. Why? Because we're holding heat down. We've observed nights are getting warmer faster than days. So we know it's not the sun. And there are many other instances like this, but there are fingerprints that tell us it's not just the warming, it's the way it occurs. So I like to bookend my talk with my prime motivations. And I showed a globe with a child holding it, but this is so important. I have to show it. This is a photograph of Earth from Apollo 17. This thing is pretty cool. This is where we live, our families, our friends, even our enemies, our pasts, our futures, our hopes, and our dreams. And it's this thing that brings us here today. It's this thing which brought me here today and brought you, Jeannie, from your beautiful home near San Francisco. Isn't that right? Excellent. So brief discussion of the greenhouse effect. Sunlight passes through the atmosphere. That's why we can see things. We can see the sunlight outside. The atmosphere, by and large, does not stop sunlight. But the Earth sends energy back. We're actually emitting energy. It's called infrared. It's sort of like light, but a different color. That energy is trapped by the atmosphere and returned to Earth. That's the greenhouse effect. The greenhouse effect would be around whether humans were here or not. If it wasn't for the greenhouse effect, the Earth would be uninhabitably cold. So the issue isn't, do we have a greenhouse effect? The issue, rather, is what happens if we make it stronger? It's sort of like you're lying in bed and you've got 2 blankets on. It makes you feel comfortable. But what happens when you add 2 more? It's the addition of our own greenhouse contribution that we're concerned about. Some people think climate change is a deck of cards. If you pull one bit of data away, it all collapses, and it's not. We've got a bunch of different independent pieces of evidence. One of them, which is particularly striking, is our neighbors, Mars, Venus, and the Earth. You would expect Mercury, Venus, and Earth. You'd expect Mercury, closest to the sun, to be the hottest. Hey, it's closest to the sun. But it turns out Mercury is 525 degrees colder than Venus. Now, how is that? Venus is further away. It should be cooler. The reason is Venus has an atmosphere that is almost all greenhouse gases. So we see the impact of greenhouse gases on our neighboring planets. So now let's go back in time. The first question I want to ask is, are greenhouse gases increasing? This curve that you see on the graph is one of the most famous graphs in all of science. It's called the Keeling curve, named after Charles David Keeling. In 1957, he began to measure carbon dioxide in the atmosphere in Hawaii and in the Antarctic. And the measurements have continued until today. He has shown a consistent increase of carbon dioxide. It's like clockwork. Every year it goes up a little bit. We're actually at about 392 right now. Now, what do those numbers mean? They're called parts per million. If you take 1 million molecules out of the atmosphere, 392 of them are going to be carbon dioxide. Now, that doesn't sound like much. Actually, it's less than 1%. And some of our climate contrarians like to say, well, it's a small amount of the atmosphere. How can it do any harm? And I would just encourage them to drink a thimbleful of arsenic. It's a small amount. How can it do you any harm? The potency of something is just as important as its concentration. So there is no doubt carbon dioxide is increasing. This graph goes back 2,000 years. On the right-hand side is today. The left-hand side is 2,000 years ago. Those are the 3 most important human-emitted greenhouse gases. Do you see a trend? The Industrial Revolution started between the 1700s and 1800s. we have a significant increase in the 3 principal human-emitted greenhouse gases, not just coincidence. On the right-hand side, I make a note that methane and nitrous oxide are more potent as a greenhouse gas compared to carbon dioxide. So why do we focus on carbon dioxide so much? Because there's much, much, much more carbon dioxide than methane. Each molecule of methane is 20 times more powerful than each molecule of carbon dioxide, but we have so much more carbon dioxide. That's why we focus on carbon dioxide principally. Of the human-emitted greenhouse gases, carbon dioxide is the most important. Methane second, and nitrous oxide's third. They're all important, but one is more important than the others. So where does it come from? Well, electricity, let's focus on that. Coal-based electricity produces about 50% of the electricity in the US, just over a third of our emissions. Our coal plants produce more CO2 than Africa and South America combined. If you read your electrical bill at the end of the month, your energy use is measured in terms of kilowatt hours. Each kilowatt hour is 2 pounds of CO2, which is 18 cubic feet of pure CO2. So imagine 18 cubic feet, take all the air out, fill it with CO2. That's for each kilowatt hour. The next source, one of the biggest sources, transportation. 1 gallon of gas burnt in a car releases 19 pounds of CO2. Now that's amazing, because that gallon of gas is a little under 7 pounds, which means the weight of CO2 coming out the tailpipe is almost 3 times heavier than the liquid you put in the gas tank. How many of you have a chemistry background? So you balance chemical equations. You're taking a carbon, you're adding 2 oxygens. So if you've done chemistry, you know how that can happen. 173 cubic feet of space for 1 gallon of gas. Now, I drove here. I'm using electricity. I'm actually contributing to the greenhouse effect. I don't put these stats on here to say we should shut down everything and go live in caves. But it's important to know the major sources if we're going to make smart and efficient solutions to solve the problem. So now we know carbon dioxide's going up. We know methane and nitrous oxide are going up. So what? If temperatures aren't going up, who cares? This is a graph, 1880s on the left, 2011 is on the right. Each black dot is an annual temperature value for the Earth. This is from NASA's Goddard Institute of Space Studies. Couple things to note. The black dots go up and down. 1 year it's hot, 1 year it's cold, 1 year it's hot, 1 year it's cold. Actually, the biggest indicator of whether you're going to go up or down is whether you're in an El Niño or La Niña cycle. The other thing to note is if you just look at the trend, it's going up. The trend is shown by the red curve underneath the black dots. The trend is going up. So 2010 was the hottest year on record. That didn't prove global warming, but it's part of a longer trend. 2011 was cool worldwide. That didn't prove global warming ended. It looks like we're entering El Niño right now, which means 2013 will likely be the hottest year on record again. 2013 will beat 2010. What you want to do is you want to look at the overall trend, and the trend is up. Here are the hottest years on record in order since 1880. Coincidence? Let's go back further. This is a graph that goes back 650,000 years. The numbers on the bottom are thousands of years. The very right-hand side is today. The black curve, second from the bottom, is temperature. I'm going to talk about how we made these measurements in a second, but just bear with me for a moment. The red is methane, the red is carbon dioxide, the blue is methane, and the green is nitrous oxide. Those are the levels of these gases that we've had for 650,000 years. In the way upper right, you see 3 stars. Those are today's levels. We're off the chart. Now, what I want you to notice is, you see those gray bands? When temperature goes up, so do the greenhouse gases. When temperature goes down, so do the greenhouse gases. In fact, if you put them on top of each other, here's what it looks like. There are 2 curves. There's a red curve, which is temperatures measured from a South Pole or Antarctic ice core, and the green curve is greenhouse gases. Correlation? Do they go together? Now, I am not saying that dinosaurs or cavemen or extinct animals had coal plants that they were burning to cause climate change. All I'm saying is the 2 go together. We call them handcuffed. When temperature moves, greenhouse gases move. When greenhouse gases move, temperature moves. They're lockstep with each other. So if someone is going to say or suggest that greenhouse gases can go up but temperatures go up, they're going against hundreds of thousands of years of evidence. So how do we make these kind of measurements? We didn't have thermometers back then. We use what are called natural proxies. And let me describe a natural proxy. Let's say you travel with Will up to northern Alaska. And you dig down into the ground and you discover fossilized palm fronds and crocodiles. What would you infer about the temperature back in time? It was warmer, right? What if you discover that, does anyone know a plant species that's characteristic of the Arctic? Lichen? Okay, what if you dig back in time in Missouri and you discover a lot of lichen? What would you infer about the climate? Cold, right? It was more comfortable. Yeah, it was cold. So we use markers from nature. We didn't have thermometers back 100,000 years, but we can use markers from nature. You can use tree rings. You can use coral growth. You can use lake sediments. But there are all these markers. One of the most important markers are ice cores. There's a photograph of someone digging out an ice core. They can go down 2 miles. There's a fantastic book on this topic by Richard Alley called 2 Mile Time Machine, written for someone like me who doesn't know anything about ice cores. And they can pull these ice cores out, and I've got a photograph of a meter-long section of the ice core. And if you're sitting near the front, you can see rings. Those are annual bands, so you can count back in time. So you can go back 100,000 years, 200,000 years. You've got time. The next thing you do is you melt that ice, because trapped in small bubbles in the ice is the atmosphere when the snow fell. So you melt the ice and you release ancient atmosphere. So now you can say how much carbon dioxide, methane, nitrous oxide, and so forth were in the atmosphere. So now you've got greenhouse gas levels. Finally, you look at the composition of the snow. There's an oxygen, what's called an isotope. Isotope just means oxygen and all other chemicals come in flavors. And the type of oxygen in the snow is a marker of the temperature when the snow fell. So you look at the isotopes to get temperature, you look at the rings to get time, you look at the bubbles to get the atmosphere, and that's how you get this curve. So, everything I've shown you to date is looking back. Can we look forward? Well, unfortunately, we don't have another Earth on the other side of the sun that we can run experiments on. So in order to project where we're going, we have to use We actually don't have to, but it is common to use computer models or computer simulations. Some skeptics say that all of climate scientists is reliant upon computer simulations, and that's actually not true. A couple years ago, Jim Hansen used a forward projection just based on past data. So you can do it, but computer models are a particularly powerful tool. And what you do is you put into the computer model the greenhouse gas levels, and you put in information about the sun and so forth, and based on the physics, you get the temperature and precipitation and so forth. Now, this is a complicated slide, but what this slide shows us is what are called emission scenarios. And I want you just to focus on two columns, A2 and B1. The very top curve of A2 is going up like this. That's emissions going through the roof, business as usual. B1, the curve goes like this. That means we pull down the emissions. So B1 is humans take action. A2 is we don't do anything. What's the impact? The impact is at the bottom. These are the temperatures. If we're on this path, we get a rise that's significant. If we're on this path, we level off. The moral of the story, the important part of this slide, the reason why I want to show it is what we do matters. What humans do matters, what path we're on matters. If we can jump off of A2, which is where we are, and get onto B1, it makes a big difference in the outcome. So don't, when people tell me it doesn't matter what we do. So this is what we've seen so far. These are temperatures going back 1,000 years. The red is today. Here's what we've seen so far. That's where we'll be by 2100. This year we had 90% of Greenland go into a melt state. We had an $80 million flood in Duluth. We have a drought in the central part of the US that's going to cost over $20 billion. We had a drought in Texas last year that cost $5.2 billion. 600,000 head of cattle had to be killed. We're seeing that with this. I want to talk about some other indicators from the natural world. This is a sketch of the North Pole. You can see Greenland. That's the ice sheet at the end of the summer melt in 1980. I should have pointed out, it's equivalent to the continental US minus Arizona. That's how much ice we had. In 2005, that's how much we lost. 2007, in 1 year, we lost that much. Northwest Passage is now open. So Arctic ice loss is happening at a staggering rate. If you go to the National Snow and Ice Data Center, they show a graph of the ice each year. This is where we're at. It's interesting, this was 2007. The next year it rose. And people said, oh, global warming's over. You don't want to get caught with an up and down year to year. You want to look at the long-term trend, which is shown by the blue line. Why do we care about ice? Because ice is reflective. When sunlight hits ice, it bounces back to Earth, keeps the Earth cool. But when global warming occurs and the ice melts, it exposes dark water, and that allows more energy to be absorbed. Scientists call it a positive feedback. That's a terrible way to describe it. Positive feedback's when my 6-year-old eats broccoli and I let her have dessert. This is a vicious cycle. It is a vicious cycle. Warming that we causes changes in the environment, which leads to more warming. Scientists have underpredicted the ice loss. Part of the reason is there were things happening scientists didn't appreciate. One is Mulans. There's a photograph, this is a famous photograph of a river of water flowing toward the photographer and going down into a hole. Let me actually show you that. That is a Mulan. I hope you can see it. It's a little river on top of an ice sheet. Now watch where it goes. It's going into a hole. Why do we care about Mulans? I'm going to show you what impact they have in a couple slides. But this is a pond. This is a lake. If you're sitting near the front, you can see a white background. That's an ice sheet. This is a lake on Greenland. That's a motorboat in a lake on an ice sheet. Why do we care about these melt ponds and Mulans? Hey, that rhymes. The water goes down underneath the ice sheet, and then it flows to the ocean, and it pulls with it the ice sheet. So it's causing more rapid ice loss than scientists had anticipated. We're going to go to the South Pole. The Antarctic is broken into two sections: the west, which is small and unstable, and the east, which is large and more stable. In the west, the warming is fast as any place on the planet. So what? So what if we lose glaciers? So what if we lose ice sheets in the South Pole? Well, aside from the impact in the ecosystem there, they're going to impact the ecosystem everywhere. Sea level rise is one of the biggest concerns that we have. This is a topological map of Asia with a focus on Bangladesh. The colors show how many meters you are above sea level. Current projections are by 2100 we'll have 4 feet of sea level rise. If scientists are wrong, they're likely to be wrong on the low side rather than the high side. Okay. Bangladesh is a country with 160 million people. We had trouble with the refugees from New Orleans, and we're the richest country in the world. What happens if you're India and you've got millions of displaced people on your border? This is the southeastern part of the US with 1 meter of sea level rise, 3, goodbye Miami, 6, goodbye southern Louisiana. But we can't have 6 meters of sea level rise, can we? Well, if Greenland were to melt, we get 7, which is 23 feet. If the western part of Antarctica melted, which is the unstable part, we get 5 meters or 17 feet. And if all of Antarctica melted, we get about 270 feet. So yeah, we can get 6 meters. By the way, when I get to this slide, I'm so depressed. I mean, you know, you make the case for the evidence and it can get depressing, but just bear with me for a little bit. We'll get to some solutions because we really can solve this problem. Some of the things that are coming are lower crop yields. Well, we're seeing that this year in the United States. It's not just going to affect developing countries. Ocean acidification. The issue of water is, and this has been predicted for a long time and we're seeing it, the rule of thumb is dry areas are going to become drier because evaporation happens faster in a warmer environment. Wet areas become wetter, and downpours occur in bigger bursts. So really 2 things are happening. 1, evaporation happens, dries things out. But 2, there's more moisture in the air, and we know that. I mean, is it more humid today, or is it more humid in January? Today. It's an obvious question, right? We know that. And that's because warm air can hold more moisture. So as we warm the air, there's going to be more and more moisture in the atmosphere. In fact, due to human warming of the Earth, we've had a 3% increase in the amount of water in the air. So we're adding more water to the air, and that's got to come down in rain or snowfall so we can get heavier rains or snows because of global warming. Now, so I work with a lot of scientists on messaging, and the scientists that I'm working with have now, we used to say you can't pin any event on climate change. Now it's a different message. It's every event is affected by climate change. So climate change, you know, the flood in Duluth may or may not have happened without climate change, but climate change made it worse. The drought this summer may or may not have happened, but climate change made it worse. So there is no weather event today in the world that is not impacted by what we're doing. Likely increase of extreme weather events. I should add here 100-year droughts. With hurricanes, the jury's still out, actually. The prevailing view is there'll be fewer but more powerful hurricanes. Fewer but more powerful. You know, I was thinking, we think we have it bad with our heat wave this year. Do you know that in 2010 in Russia, it was so bad and there were so many fires that the weather report in Moscow was smoke? What's the way? Overcast? No. Sunny? No. Smoke. Invasive species, migration of flora, and extinctions. Okay. The Olympics are almost over. If we had an Olympics of emissions, we would be gold medal winners. Canada and Australia per capita, this is per capita, they are close behind us, but we are the gold medal winners so far. If you look at us by country, if you take all the CO2 in the atmosphere, we are responsible for 28% of it. Now, other nations are gaining on us. In fact, this year, China will out-emit us. But CO2 stays in the atmosphere for a long time, so most of what's in the atmosphere causing the warming has been emitted over the past decades. And we just have had a long history of emission. What do we do? Do we just come to the Will Steger Foundation and eat some bagels and have coffee? I mean, this is where we're going. This is in gigatons of carbon dioxide. 1.8 is where we're at. 2.6 is where we're headed. Do we wait for a silver bullet? Engineers or scientists will save us? I don't think so. I think we do silver buckshot. You add a bunch of things together that make a big impact. And these things make sense. Increased energy efficiency in our homes, in our cars. Increase of renewable energy development. Reforestation. We don't need cold fusion to solve this problem. We can solve it with today's technology. About 20% of emissions are due to deforestation. Don't tell me we don't know how to plant trees. Yes, ma'am. This is from a paper done in 2004 which did the analysis on these wedges. These are called the emission wedges. But actually there are wedges that aren't even included here. I mean, for example, they don't have reforestation. Okay? These things make sense anyways. My car gets 50 miles a gallon. When my wife drives it, it gets 60. I drive a little faster. When gas goes to $5, $4 a gallon, I couldn't care less. You know the impact to me? I have more money in my wallet. If you get power from Excel, you could sign up for their wind source program and get your energy through wind power. My household gets all of its energy through wind power. It costs us about $1 to $2 extra a month. We've just eliminated our biggest contribution. Use energy more wisely. You know, insulate your house. Put on a low-flow shower head. I mean, these things are common sense, and they save money. And I'll tell you, I've had many of my conservative friends and family members downplay this. But my grandmother was conservative, and she saved every button that fell off every shirt, and she put it in a tin, and that button would find use. If any shirt had a hole, it would be sewn into something else. Waste is not a conservative value, and I think people need to be reminded of that. What can you do? The most important thing we can do is have a national energy policy, so talk to your representatives at the state or national level. At the state level, we're being sued by North Dakota over our prohibition of their new coal power plant lines running through our state. Tell your representative you want to fight that lawsuit. Tell them this issue is important to you. If an official gets 1 or 2 phone calls, it's some cranks. If they get 5 or 6, it's a groundswell. Talk to your families and friends. Make sure they know this is important to you. You can reduce your own home usage. You can get a home energy audit. I got one 2 years ago. Within the first year, saved all the money of the installation and the audit. Reduce transportation. And then call me. If you've got a question about the science, give me a call. Path forward's clear. I would rather pay a farmer in southwestern Minnesota for that than send sons and daughters to fight for oil in Iraq or have to clean up a spill from that. It makes sense. It just makes sense, and change is possible. I love the photograph on the left. It's a rusty old oil well in the foreground, beautiful wind turbines in the background. The guy on the right, he's an entrepreneur, algae-based biofuel, taking algae, making gasoline. So I run a climate rapid response team. Here's some screenshots of our website. We have this website so people in the media can ask questions. They submit it online. I showed a picture of the Earth from Apollo 17. That's one of the reasons why I come to events like this. I've got these 2 other reasons. Olivia's my wild child. She's 6. She's pensive. She's thoughtful. She's going to be the scientist. I'm sorry. No, Olivia is not my wild child. Lily is my wild child. Olivia is the calm one. This is the wild one. She's the one who woke me up at 4 o'clock this morning, wanted to go to the bakery. Don't tell Mom. My daughters are going to ask me 1 of 2 questions when they get older. They're going to say, how did you let this happen? You knew it was going to happen. Or they're going to say, how did your generation find the uncommon courage to take action to preserve this world for us? And I desperately want my daughters, and now my 3rd daughter, shown in the figure here, to ask me that second question. So that's why I'm here. Avery, my new daughter, is going to give Lily a run for her money in wildness. Last slide. So I train climate scientists to give talks, to do radio interviews, print media interviews, etc. We teach them messaging. It's really simple. It's 1 slide. This is how you handle just about any situation. Parent, student, administration, colleague. These are the key messages. We know it's happening. We've known it for 150 years. Scientists know. This isn't new. The first prediction of how much the Earth would warm with carbon dioxide doubling was in the 1800s. We've got a problem, but we can solve it today. We can solve it with today's technology. And if we solve the problem, there's going to be a bunch of other benefits. Not only can we save the environment, we can conserve energy. We can fill our pocketbooks. We can improve national defense. The Department of Defense is one of the biggest allies in this issue. They are all over this issue. They've identified it as their critical risk in the coming century. They have sent their generals to testify to Congress saying, take action. If the Department of Defense thinks it's a risk, the rest of us should think it's a risk. And even if you don't care about saving the planet, you should care about energy. I mean, a gallon of gas. Who makes oil? It's a trick question. No one. Microbes made it millions of years ago. We are using a non-renewable resource that's really valuable. A gallon of oil has so much energy, it can take an SUV, move it 60 miles an hour for 20 miles. How many cheeseburgers would you have to eat to have that kind of energy? It's magic. Let's use it wisely. Let's not waste it. So there's these other benefits. We can create jobs. Wind, solar power in the United States. The wind industry employs more people than coal, by the way. And this last point is especially telling today. There is a cost to do nothing. Don't let someone tell you it's too costly to do something. The drought last year in Texas cost every working Texan over $500 out of their own pocket. 600,000 cattle had to be killed. The drought this year, $20 billion to our nation. And this is just the beginning. It is going to cost to do nothing. It is more financially, fiscally conservative to take action now. The longer we wait, the more difficult it will be. So, there's a path forward. We have a problem, but there's a path forward. And if we can convey the multiple reasons why we would embark on this path together, I think that we can get there. And that concludes the formal part of my talk. I'm happy to take any questions people may have. I just want to say a word of thank you. You all are doing something very, very important. And I want you to know that scientists are here to help you, to complement what you do. And if there is any way that we can provide information or provide ways of discussing this in your spheres, we'd be happy to help. It's a great pleasure and an honor, and I'm going to turn the floor over to someone, I'm sure. Thanks.